Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we go into the 5.1 to 5.3 quiz in the Big Ideas Math Integrated Math 2 textbook. It's a review of 15 questions. You probably want to get the calculator ready, and if you'd like to download this thing, you can find it in the description section and find each individual problem if you'd like by checking the timestamps and clicking on those individual ones. You know, 5.1 to 5.3 have been quite an adventure even for myself. There are things where I'll question my own doing with these things. I can be rusty with statistics, and the questions can all be varied depending on how they are, and it's just good to have that conversational piece, you know? As long as they are, I make sense of it when I talk about it more. So if I talk about it more from this stuff here, and if it's longer, that's just the nature of these problems as they can be. There are formulas, and maybe if we have the formula down pat, we can go into it. I'm just hoping for very little sample space, writing out like 50 different things on a sample space, but we'll see how they go. Without further ado, let's go ahead and get started and see what we're dealing with here. We are dealing with number 1. Out of section 5.1, where it says you randomly draw a marble out of a bag. Hold on, I need to brighten my own screen. Out of a bag containing 8 green marbles, 4 blue marbles, 12 yellow marbles, and 10 red marbles. Find the probability of drawing a marble that is not yellow. So finding the probability of not yellow, and we kind of put this like yellow with a bar, I guess we can say. It's going to be 1 minus the probability of having a yellow, and I think that's the fastest way of saying it here. So, because 100% of everything minus the probability of just yellow is everything else that's not yellow. So, probability of yellow, there are 12 yellow marbles, and in total, there are 8 green, 4 blue, the 12 yellow, and 10 red. So, we're looking at 1 minus 12 over 34? 34 minus 12, because now it's 34 over 34, and 34 minus 12 is 22. So 22 out of 34 is that value. Now I can reduce that fraction to 11 out of 17, and we can write it like that. We can do a decimal equivalent. We can do the, normally we're doing like 3 decimal places. We can also do a percentage. So if I do 11 divided by 17, I'm getting 0.647, so around 64.7%. So this is 64.7% chance you don't draw yellow, which means everything else, the 35 some odd percent, is the probability that you do draw yellow. Yellow is the most prevalent marble in the bag. All right, number 2, find probability of A naught. And I think that's kind of what we were just doing, right? So, or numbers 2, 3, and 4 were doing it. So probability of A, we didn't really get questions that were straight up like this in the textbook. A naught, find it. Or we did, and it was just that quick, and I just don't remember. It came in like a flash. So yeah, just 1 minus the value. That actually started with the first one. So it's interesting that we're kind of doing that here still too, with 2, 3, and 4. 3 questions of this format. Very, very interesting. Probability of A in this case is 8/9, and probability of A naught. And I'll keep it in the format that they have it written, meaning if this is a fraction, I'll keep it as a fraction. It's a percentage, I'll turn it into a percentage. So 1 minus 8/9 is going to be 1/9. So not A. I shouldn't say A naught. I believe we say A bar. A bar. A naught is like A initial. I just realized that. Number 4, probability of A is 0.01. I was thinking not A, if that makes sense. 0.01 probability of not A, or A bar, is 1 minus 0.01. Very interesting set of questions. Listen, I'll be honest. Once again, why I just said all this, I don't remember this set of questions in that section specifically. Not much less that we have 3 of them in a 15 question set on a quiz review. And the first question was one of those not questions if you're doing it right. So unless I'm doing something wrong with those problems, that's an interesting set and the fastest set that we've had so far in the entire chapter. Number 5. You roll a 6-sided die 30 times. A 5 is rolled 8 times. What's the theoretical probability of rolling a 5? So I'll write probability of 5 theoretical. A 6-sided die, they have an equal likelihood of, occurring there, and that's just going to be 1/6. We'll leave it to that. What's the experimental probability of rolling a 5? That's after we did the experiment itself, and that rolled 8 times out of 30. Now, 8 times out of 30 is 4 out of 15. I feel like we want to do a nice direct comparison of these as well. 1/6, isn't that 16.7%, I believe? And 4 out of 15, I do not know. 4 out of 15 is 26.7%. The reason I bring those up is in case they said make a comparison between the two, how the experimental compared to it. And the experimental showed up this many times more or whatever, this much percent more. They didn't ask, so I won't answer, but it was more prevalent. Let's reduce this fraction first. Always reduce your fractions if you're able to, unless they're asking straight up for decimals or percentages only. Number 6, you randomly draw one card from a standard deck of 52 playing cards. What are the odds that it is a diamond? All right, so you need to know that there are 4 suits: diamonds, clubs, hearts, and spades. They're all equal likely chance of occurring. So as far as diamond goes, probability of diamond is, you can say it one of two ways. There are 13 diamonds in the deck out of 52, but when you reduce it, ultimately you get 1/4. That's also 25%. Oh, that's a part A. Part B, it's like a fly in my room. Part B, what are the odds that it is a 7? Probability of 7, there are 4 7s within the overall set because there's 7 of diamonds, clubs, hearts, and spades. So 4 out of 52, and that one reduces to 1 out of 13. 1 per suit, and there are 13 cards in each suit. So I'll leave those as fractions. I think that that's standard play for card draws. Probably should have done the same for dice rolls. Number 7. Events A and B are independent. Find the missing probability. We're given that the probability of A is 0.25. Probability of B is unknown. That's the missing one. And probability of A and B is 0.05. Okay, in an independent case, when you find the probability of A and B, it's going to be the probability of A times the probability of B. If that's the case, if they're independent, this is what you can do, straight up multiply them. So we have 0.05 equal to 0.25 times the probability of B. So to find the probability of B, we're going to divide both sides by 0.25. 0.25. So 0.05 divided by 0.25, that's a fifth of it. So probability of B should be 0.2. Should be 1/5, but 0.2. If those are decimals, I want to leave this one as a decimal as well. Yes. All right, that's number 7. Number 8. This is going very fast. Man, if you've been with me in the lecture portion, first of all, the lectures have been long, but the sections themselves, these questions would go incredibly slow. I didn't see what we're asking. Events A and B are dependent. Find the missing probability. Probability of A is 0.6. Probability of B given A is 0.2. And the probability of A and B is blank, is unknown. So in this case here, for a dependent case, the probability of A and B will be the product of these two that you're looking at. Probability of A times probability of B given A. What we're looking at here, a dependent case, and I didn't really state it for independent right now. An independent case means that a future event's probability is not affected by a previous outcome. So if I flip a coin and I land on heads, that doesn't increase or decrease my probability of landing on heads in the future. But in a dependent event, it means a future outcome's probability is dependent on what your previous outcome was. So if I did draw a card and didn't put the card back in the deck, then it's changed the probability of any other card that's drawn within here. It's increased their chance of being drawn because there are less cards and maybe less of that kind of card or more of that kind of card, whatever, in comparison. So probability of A and B, what they're saying here is that we take the probability of something that the probability that something occurs, and let's say you're successful in that happening. Okay, if that happens, now the probability that B occurs given that A occurred is 0.2. We don't know what probability of B would be without that, or at least we don't have that information, and we're not trying to figure that out. But what's the probability of both A and B occurring? Once A occurs, here's B's chance of occurring, and that's going to be 0.12. I know I spent a little more time on that, but because they weren't necessarily bringing that up, and I don't know if they'll bring it up again, I really wanted to cover it. Okay, I'll just flip the thing because it looks like 9, 10, 11 are part of the same thing. Numbers 9 through 11, you roll a red six-sided die and a blue six-sided die. Find the probability. Probability of red odd and blue odd for 9, red and blue both less than 3 for 10. So I wanted to check on these three because I wanted to talk about independent and dependent again. If I roll this die and roll this die here, first of all, rolling die generally are an independent case, but rolling one die and landing on some outcome should not affect the other. So these are all independent probabilities. So we're going to treat them like the independent formula you had. So probability of red odd and blue odd. Are these standard six-sided die? Yes, they are. That's going to be probability of red times probability, red odd, I should say, times probability of blue odd. Now, I might not write this one on the next problem like this. I'm just showing you that that's what we're actually multiplying. Probability of a red odd. Your set in your sample space, here are the different numbers that occur. I know we didn't list things before, so I want to list it now. Here are the different numbers that occur, and 1, 2, 3 of them are odd numbers out of the 6. So 3 out of 6 probability that you land on a red odd, and same with the blue. Doesn't matter that it's blue or red. It's just saying that they're different die, and they want to make sure that you know that. Independent event. 3 6 times 3 6 is 1/2 times 1/2. That is 1/4. Now that we're talking about like dice rolls and stuff, I'm going to go ahead and write different things like 25%. 0.25 is 25%. Number 10, probability of red and blue both less than 3. So I still have this sample space. We might as well refer to it since we have it. So less than 3, there are 2 of 6 numbers that are less than 3. And since they both have to be less than 3, then we'll do that. Probability of red and blue both less than 3. So that is going to be 2/6 times 2/6, or 1/3 times 1/3, which is 1/9. Sorry for the scattered writing. 1/9, which is about, percentage-wise, 11.1%, because it's 0.1 repeating. So 11.1%, or 1/9. Excuse me. Number 11, probability of a red 2 and blue being greater than 1. So probability of red 2 and then blue greater than 1. So probability of a red 2, how many, 2 out of, well, it's not 2 out of, but this 2 is a single number out of 6 numbers. So that's a 1/6 chance of landing on 2, just like any other one. Blue greater than 1, there are 5 numbers greater than 1. 2, 3, 4, 5, 6. That's 5/6. 1/6 times 5/6 is 5/36, and I do not know what that decimal is. So let's check it out. 5 divided by 36. 0.138 repeating, so around 13.9%. There you have it. 4 more questions, so hopefully this thing kind of stays at this speed. It looks like it will not. Numbers 12, 13, 14, 15. Here we go. Number 12. In number 12, it says, a survey asks 13-year-old and 15-year-old students about their eating habits. 400 students are surveyed, 100 male students and 100 female students from each age group. Okay, yeah, that's 400. I got it. The bar graph shows the number of students who said they eat fruit every day. I think I lost my drink. I wanted to get some water. The bar graph shows the number of students who said they eat fruit every day. So we have, among the 13-year-olds, the female is the darker color one right here. Male is the lighter one, and same here among 15-year-olds. And there are 100 of each, they said. 100 females and 100 males, I think they said. Oh, from each age group. The bar graph shows numbers who said they eat fruit every day. So there are some who don't eat fruit every day that are not displayed on the bar graph. That's what I was trying to make happen. All right, find the probability a female student chosen at random from the student surveyed eats fruit every day. So that a female student chosen at random. They're not saying that any student chosen at random. So we're talking about given that we have a female, they eat fruit. So fruit given female. Now, I don't know if you can see this bar graph enough to be able to see what the numbers are. But what we got to do, first of all, is we have to find the probability that they eat fruit and are female. Let me kind of write that. Probability of fruit and female. And then we got to divide by the probability of all females. Or you can probably just look at the amount divided by the amount in some cases. I'll show you that those should both work. Because you're dividing by the same results, you're still dividing by 400. So, and maybe we should just do that, really. Because, where's the females? So, 100 male students, 100 female students from each age group. So, it doesn't have to do with age here. A female student chosen at random. I have 60, 62. I have 61 13-year-old female students and 58 15-year-old female students. So number of females, these are ones who eat fruit, by the way. Number of female fruits is 61 plus 58, which is 119. Now there are 200 total females. So what I want to say there, so our probability, I'll just put P, 119 out of the 200. See, I shouldn't have to do 119 out of 400 divided by 200 out of 400. If they're both out of the same amount, 400, this is it. Out of all 200 females, how many eat fruit? 119. So when you divide that, that should be 59.5%, I believe. 59.5% for number 12. Is there a part B? Oh, part B. Find the probability that a 15-year-old student chosen at random from the students surveyed eats fruit every day. So now we're only looking at the 15-year-olds. So let's come up with that first. Number of 15-year-olds. And I have, I think, 53 male and 58 female. So 53 plus 58, and that is 111. 111 15-year-olds. Probability that a 15-year-old student chosen at random eats fruit every day. Now we want to find the fruit eaters among the 15-year-olds. Oh, shoot. Hold on a second. Those are 15-year-olds who eat fruit. That's 15-year-old fruit. We have to find out how many 15-year-olds there are. There are 100 from each group, so I guess there are 200 total of that as well. So, 15-year-olds who eat fruit is that. So that's also divided by 200 because there are 100 from each group. 100 male 13-year-olds, 100 female 13-year-olds, 100 male 15-year-olds, and 100 female 15-year-olds. So 200. So, probability of eat fruit given that you are 15 is going to be 111 divided by 200. See, this problem so far seems more like what I was doing a lot of. I think it's 55.5%. Seems a lot more like what I was doing in the textbook stuff. Having the conversation matters in these cases when I call these things out here. Number 13. At school, 55% of students use public transportation. 25%, I don't know why they had one write 55 and the other spell out. Anyway, 25% of students use public transportation and participate in an extracurricular activity after school. What's the probability that a student who uses public transportation also participates in extracurricular activity after school? So this is still that same division, only this time I can actually use it as probability because that's what they have. We want to find probability that you participate in extracurricular activity. So activity given that you use public transportation. That will equal the probability. So what you have to do is take all of those who do both, right? Probability of activity and public transportation, and only divide it by those who use public transportation. Remember, it is given those who use public transportation. We don't care about those who do not for this question, and we only want to look within those who use public transportation and do activities, extracurricular activities. So we have those numbers as 25%, so I'll use 0.25 of those do both, and then of those 55% there, so 25 out of 55. It's 5 out of 11. It should be is that 454545? Let me see. I'll just actually do 0.25 by 0.55. I don't want to get it wrong. yeah, 0.454545. So I'll say the percentage, 45.5%. That's approximated. The other ones were exact, by the way, the 55.5 and stuff. So I should probably use that one. Boom. All right, two more. Number 14. There are 14 boys and 18 girls in a class. The teacher allows the students to vote whether they want to take a test on Friday or on Monday. That sounds like something I would do for my students. A total of 6 boys and 10... Oh, it sounds like a two-way table. A total of 6 boys and 10 girls vote to take the test on Friday. Organize the information in a two-way table, then find and interpret the marginal frequencies. Let me pause for a sec. When I did 5-3, I kind of made a two-way table thingy, like template. Let me pop that up. Hold on. Okay, if you followed along with me in section 5.3, this should look familiar when I created it at the time. So, okay, we have boys and girls and about taking the test on Friday or Monday. So I'm not really writing the categories. I'm just separating the categories. So boys and girls test on Friday versus test on Monday. So with a two-way table, we also have the totals. They just want the frequencies and they want to interpret them. No relative frequencies, just marginal. 14 total boys, 18 total girls means 32 students total. A total of 6 boys and 10 girls vote to take the test on Friday. 6 boys and 10 girls. That means 16 total students of the 32. That also means 16 vote to do it on Monday. Does that mean another 6 boys and 10 girls? No, not necessarily. In fact, 6 plus what is 14? That's 8. 8 boys voted for Monday, and then 8 girls voted for Tuesday. So an even split here, but then less boys than girls in that scenario. Now, they did ask to interpret the marginal frequencies, and I believe that they're referring to, I guess, the Friday and Monday parts. So an even split of 16 students, of 16 and 16, voted to take the test on Friday and Monday, respectively. So right down the middle, 16 on Friday, 16 on Monday. I think that that's all they wanted for marginal frequencies. There are 32 students total. I think that can now be implied with that information. But now that we got it, there it is. All right, let's do one more question here on number 15. 3 schools compete in a cross-country invitational. Of the 15 athletes on your team, 9 achieved their goal times. Of the 20 athletes on the home team, 6 achieved their goal times. On your rival's team, 8 of the 13 achieved the goal times organized in a two-way table. So the only problem with my two-way table thing that I just made is, let's see, let me find out if I can do this. Give me, hold on, let me copy, oh boy. See, mine's a 2x2 right now. Can I add a third column or row or whatever? I guess a third row. Can I add a third row in this set? Because I didn't try last time. Let me see if I can do an insert. I might not be able to. Oh, insert row. Oh, that kind of worked. I just have to do them individually. Okay, I think I can do this. Cool. Because it says 3 schools. Okay, it won't let me click on this the way I want to. For some reason, it won't let me click on that. Is that... Okay, that was in the way, I see. Insert row. And... yeah. Totally. There's just another box there now. Something kind of went wrong there. Insert row. Okay, sorry about that. I have to work with this the way that I want to. I want to hide that one piece in the corner. So, there we go. Okay. That's kind of within what I wanted to get. All right. So I want to do... Oh, did that change anything? Oh, total. I see. Whoa, that was weird. Okay, let's go. Your school. Your versus home versus rival. And then, what was it? Achieved goal times. Achieve. No achieve. Okay. 3 schools compete. Of the 15 athletes on your team, 9 achieve their goal times. Of the 20 on the home team, 6 achieve their goal time. On your rival's team, 8 of the 13 achieved their goal time. Organize the information into a table. Okay, boom. 14 and 5 did not achieve. Totals here, 9 plus 6 plus 8. 6 plus 14 is 25. 23 plus 25 is 48. 15 plus 20 plus 13 is 48. So 48 total participants in the cross-country invitational. Then determine the probability that a randomly selected runner who achieves his or her goal time is from your school. So we're only looking for the achieved ones, and we're going to do a conditional relative probability from your school. So probability of your school given that they achieved. So we're going to take 9 out of the 23 total that are from that set. And 9 out of 23 is about 39.1%. 39.1%. So listen, this stuff, because that was the last question, this stuff seemed significantly, I don't know, easier than what we had in previous ones. So I don't know, that's just, it was shorter, it was lesser than, it was less that was asked of us as a whole. But yeah, for the thumbnail, guys, that was pretty good. And guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. So this was the first half of the probability stuff. We're going to dive into a lot more later. Take care. I will see you in that next one.